Hey everyone, my name is Ajay and this is our part 9. Today we are going to talk about Viptela data plane and its encryption. Before we talk about the SD-WAN data plane encryption, let's try to understand the IP6 peering on the traditional network. So when we talk about the IP6, why do we use the IP6? That's the first question comes. So basically we are building a tunnel over the untrusted media like internet. So there are two phases involved in forming the IP6 tunnel, which is going to be the IK phase 1 and then IP6 phase 2. So in a phase 1, it is going to build or authenticate the peers, and then is going to build the IP6 phase 2, where exactly the data encryption happens. So in this example, if you look at my screen, I have 5 devices. So let's try to start with this. Device 1, device 3, and device 2. So initially, if I have only 3 devices, how many tunnels, first of all, I'm going to form? So this is going to be a calculation. The total number of tunnel is going to be n into n minus 1 divided by 2. So if I have 3 devices only, it is going to form only 3 tunnel to build a full mesh tunnel fashion, which is my first tunnel, second tunnel, and the one which is marked in the green, that is going to be my third tunnel. As we add the fourth device, so let's say I'm adding additional device, device 4. Now if I calculate the total number of tunnel, it is going to be 6 tunnels. Similarly, if I add one more device, which is going to be the fifth device in this network, I will end up having 10 tunnels. So it's a kind of the organic growth in terms of the total number of tunnels. To establish security association, each device exchanges the key with every other devices in the network and creates per pair key. So when I say per pair, means it's going to be the key exchange between two devices. If I have many devices in the network, it is going to do the per pair key. So it is going to be generating a unique key for each remote device. This scheme means that in a fully meshed network, each device has to manage n to the power 2 key exchanges and n minus 1 keys. So for example, in a 1000 node network, when I say 1000 node means the number of devices are going to be 1000. There are going to be this much of key exchange to authenticate these devices, and each node will be responsible for maintaining and managing 999 keys. That's huge. It's very complex. Let's now understand when we talk about IDH groups. So DH groups are basically the Diffie-Hellman groups. They are responsible for generating the shared secrets. So let's try to understand how it works. So for example, this is my router 1, or maybe it's a kind of the firewall device, or this is my another device. And I'm trying to form a tunnel between these two devices. So how the DH group basically functions. So to make it very simple, let's assume this router is going to have its own private key and a public key. Similarly, here also I'm going to have my private key and public key. When I say private key, it's a private. I'm not going to share that across network. But the public keys, those can be shared. So I can see my first public key, which is shared to my peer. Similarly, here I see my public key got shared to my peer. Now I have my private key and the public key which is coming from the remote. Very similarly here, this is a remote public key and this is my private key. So with some mathematic calculation, it is going to generate a Diffie-Hellman key, both the sides. And this Diffie-Hellman key will further rely on the phase one parameter, and again with some mathematics formula it is going to generate a shared key on the phase one, and based on the phase two parameter it is going to generate a shared key for phase two. The same thing happens here at, and what we are going to see, this shared P1 and P2 keys are same. So it is going to use a symmetric method with the same key. So whatever the encryption decryption happens, they both know the key. So it can encrypt data with this key. Since I know this key, I can further decrypt the data. So this is a symmetric encryption and decryption method which works with the DH. Now let's talk about the key exchange which happens on the SD-WAN Viptela platform. I already mentioned in my previous series that it's a I-class. So it's not going to have the phase one, which is driven from the IC to generate those kind of the DH keys. So it's an I-class. Now it is going to directly generate the encryption key for phase two. So let's try to understand how it works. So encryption keys are generated per transport basis. So for example, if I have two transport, this is my T1 and this is my T2. So I'm going to generate two keys. So if you look at my diagram, this is locally generated keys. So for example, if I say encryption key, that is for the T1, and this is encryption key 2, which is for the T2. These encryption keys goes to vSmart as a OMP update, and then these vSmart, it is going to further distribute all these key to rest of the VHS devices in your network. So we can see on both end, this is my locally generated key and this is my received key, which is coming from my remote peer, where I can see these are the key which is locally generated. Let's try to understand how this key exchange happen and how exactly the encryption and decryption will look like. So look at my diagram. I have a device which is the V1, which is a VH1. On the other end, I have a V2 device, which is a VH2 device. I'm going to have a locally generated key, which is going to be the key 1. And on the remote, I'm going to have a key 2, which is locally generated. Now there is going to be the key exchange. So this L1 will go on the peer. Similarly, this key 2, which is locally generated, will go on the peer from the vSmart via OMP updates. At last, you are going to have, or maybe these both the peers will have keys. So I can see this is my key 2, which becomes remote here. So R means remote, L means is local. Similarly, on the remote end, the key 1, which is coming from V1, that becomes remote, and key 2 is the locally generated. Since it is per transport, so this is for the T1. Very similar thing is going to happen for T3 and T4 also. So for T3, this is key 3, which is going to be the locally generated, and this is coming from the remote. Very similar to what we have seen for the T1. Now what happens when we do send the data across all these IP6 tunnels? It's a bit different than the traditional IPsec method. In the traditional IPsec method, we have used the symmetric key, which is the same key being used for encryption and decryption. Here, we are using symmetric key in an asymmetric fashion. So what that mean? Whenever I'm sending data from V1 to V2, I'm going to have that encryption done by V2's key, which I received. That's going to be the remote. Once I receive that data on the V2, since I have that key because that's my local key, which I shared, I can do very well the decryption of the data. Similarly, when V2 try to send data to V1, I'm going to encrypt that data with V1's key. And when V1 receive this data, it can decrypt the data with its own key, which is going to be the local. In the demo section, we are going to follow this network topology. So this is my CL2VH1 device, which is connected to two different transport. One is internet and MPLS. Similarly, this is my BR3VH1 device. This is a branch setup, which is connected to internet and MPLS. So there are going to be two transport, both the sides. Let's do some verification on the VH devices to check the local security association. So I'm on the VR3 VS1. If I run a command which is show IPsec local-SA, it is going to tell you there are two keys generated per TLOC basis. The first TLOC is going to be MPLS, second TLOC is going to be your public internet. And this is security parameter index 256, 258. My source IP is 5.2 and another IP is 5.200. There are going to be the keys generated and this is the hashed value. Similarly, you can run this same command on the remote and you can see the hash value got generated. We can also check about the inbound and outbound IPsec connections. You need to issue a command which is going to be the show IPsec outbound connections. And you can also check the inbound connection with show IPsec inbound connections. So when we look at the outbound connection, by definition, it is going to display information about the IPsec connections to remote routers. So this is my source. This is my source port. This is my destination. This is my destination port. This is my security index 261. My tunnel MTU, which is auto negotiated, is 1442. My remote TLOC is 70. That is going to be the device on the Colo 2 VH. And the remote color is public internet. My hashed key is 6590. My authentication method is AHSHA1 HMAC. My encryption is AES 256. Similarly, if I issue an inbound connection, this is my source 1.2. This is my port, destination IP address. And what it means by the inbound connection, it displays information about the IPsec tunnel that is originate on the remote routers. So it is coming from the remote. This is my remote TLOC address. My color is MPLS. My local TLOC address is 0.81, which is the system ID of BR3. My local TLOC color is MPLS. My encryption negotiated is AES 256. Let's do some more investigation on inbound and outbound connection. So on my Colo device, which is the CL2VH1, if I issue a command show IPsec, outbound connection means the connection which is initiated from CL2 to the remote site. I'm including 0.81. This is going to be the branch 3. So I can see there are two connections basically. One is on public internet, another one is on MPLS, and that is what is expected also. Now I see there are two hashed value, key hash, and these key hash values are same values what we see on the remote device, which is going to be the show IPsec local SA. So it matches. Now let's talk about the key lifetime. So each key lifetime is 24 hours, and each WAN edge router will regenerate as a key every 12 hours in order to provide enhanced encryption and authentication. That means that two keys, old and the new one, can coexist at any given time. If you look at my screen, I issued a command show IP6 local SA. There was no, this was a new lab, so there was no regeneration of the keys happened so far. So I see two SPI index 256 and 258, and this is the key hash value. This command can also be used, for example, let's assume you want to regenerate new keys forcefully. So what you're going to do, you're going to issue a command which is going to be the request security IPsec rekey. That is immediately going to generate a new key. Now if I issue the same command again, which is going to be the show IPsec local SA, I can see two more indexes got generated. So 256, 258 I already had. Now there's an increment of 1. So my MPLS key, the next key is 257 and the public internet is 259. So I can see total 4 keys and they will coexist until the timeout happens. You also have options to set the rekey timer. So under the VH config mode, you can set the security IPsec rekey seconds. Thank you everyone for watching. I will see you in the next video.